Good morning. Thank you for the introduction. I was given just a minute.
Second. He'll tell us when he's ready.
Okay, perfect.
Looks like you got the thumbs up.
All right.
You're good.
The button?
That one's going to go.
Okay, thank you. All right, so we very recently had the opportunity to complete a Vadose soil PFOS leaching evaluation to support the groundwater remediation strategy at a firefighter training facility in Southeast Florida. And I'm excited to share some of the details with you through this talk. During the talk, I'll briefly present soil excavation as remediation strategy, give an overview of our project site that includes potential excavation scenarios, describe development of the model that we use to evaluate soil leaching under these excavation scenarios, and share the results and findings from the evaluation, and finally present some conclusions about this tool. So PFAS remediation technology is continually evolving. However, soil excavation remains a simple and effective strategy to remediate PFAS contamination in Vadose soil. For any groundwater that is recharged by water passing through impacted soils, soil remediation plays a key role in an effective groundwater remediation strategy. At a number of firefighter training facilities across the state, we have supported the FDEP with soil excavations to remediate sites with groundwater PFAS contamination. Soil removal to provisional leachability criteria is a conservative approach to PFAS mass reduction, but may not be the appropriate strategy in some cases, and so having another tool to evaluate the effectiveness of potential excavation scenarios at the pre-design stage would support a more effective cleanup outcomes. The project site we'll be discussing today is a state-owned active firefighting training facility on the Southeast Florida coast, shown here in figure. Approximately 5 to 10 gallons of aqueous film-forming foam, or AFFF, has been historically used at the site 4 times per year as part of the training exercises. The AFFF usage area is shown on the figure in that green area. There are soil and groundwater PFAS concentrations greater than provisional cleanup target levels at the site, and so I'll be referring to those, and those are state cleanup target levels. Additionally, surface water PFOS concentrations greater than the screening level of 10 nanograms per liter have also been identified in low-lying areas adjacent to the AFFF usage area and in a creek that bounds the facility to the east. At our site, shallow groundwater generally flows across the site towards that creek to the east. As part of site assessment activities, we have advanced over 100 soil borings to delineate Vadose soil PFAS contamination. And so in the figure, you can see little yellow triangles, and those are soil borings with exceedances. Maximum soil concentrations for PFOS and PFOA are 270 micrograms per kilogram and 19 micrograms per kilogram, respectively. The highest soil concentrations observed at the site are within the AFFF usage area, and this represents the main source area. The water table at site is approximately 7 feet below land surface, and based on our assessment, we estimate there's approximately 5,900 tons of soil with PFAS concentrations greater than provisional leachability soil cleanup target levels, which are 7 micrograms per kilogram for PFOS and 2 micrograms per kilogram for PFOA. We have installed more than 70 wells across the site to delineate groundwater PFAS contamination to the provisional groundwater cleanup target level of 70 nanograms per liter, or parts per trillion. And that's shown here in the figure. The yellow contour is the 70 nanogram per liter contour. Maximum recent groundwater concentrations for PFOS and PFOA at the site are 3,200 nanograms per liter and 670 nanograms per liter, respectively. The highest groundwater concentrations observed at the site are within and down gradient from the AFFF usage area. And those groundwater impacts primarily occur from the water table to a depth of about 40 feet below surface. Despite most of the soil impacts being limited to the AFFF usage area, we do have a relatively broad and shallow groundwater plume that extends far up gradient from the AFFF usage area. We have also observed surface water PFOS concentrations up to 22 nanograms per liter in the nearby creek that's down gradient from our groundwater plume. The current remedial objective for our site is to mitigate the potential for migration of contaminated groundwater to that creek that borders the site to the east. To address that objective of mitigating groundwater impacts migrating toward that creek, a key question we had to ask is, what is the contribution of soil leaching to groundwater? And if we were to consider excavation as a remedial strategy, what would be the benefit of doing that to groundwater? We developed 3 soil excavation scenarios to evaluate potential benefit to groundwater using a Vadose leaching model. The first scenario that we modeled would consider the contribution of soil leachate recharging to groundwater as conditions exist and assume nothing was done to remediate the soil. The second scenario would consider the contribution of soil leaching to groundwater if we were to remove soils with PFAS concentrations greater than provisional leachability soil cleanup target levels. And just for reference, that the extent of those soils that we would remove under this scenario is shown as that dark orange polygon. The third scenario would consider the contribution of soil leaching to groundwater if we were to remove soils with average PFAS concentrations greater than 5 times the provisional leachability soil cleanup target level, so kind of increasing that threshold a little bit. And this is a number without any regulatory significance, rather it's a higher threshold that we've derived from a correlation between soil PFAS concentrations and groundwater impacts observed at the site. Essentially looking at excavating the extent of the soil borings located within the area where groundwater concentrations are at least 10 times the provisional GCTL, which is shown in as that red contour. This scenario kind of asks the questions, can we remove less soil and therefore spend less money and still address our remedial objective? So this excavation scenario would remove 3,600 tons of soil compared to the full excavation of 5,900 tons. All right, so going into our model design, the Vadose leaching model used in this evaluation is a one-dimensional model that simulates PFAS retention in the Vadose zone. It models flow through the Vadose zone combined with chemical transport mechanisms that include adsorption to organic carbon and adsorption to the air-water interface to simulate leachate concentrations, which is essentially the PFOS concentration of the water that ultimately recharges to groundwater. In this evaluation, we specifically simulated PFOS concentrations in soil and leachate, since for our site, PFOS was the main driver of the extent of PFAS contamination in both soil and groundwater. As part of the model development process, we did have to collect some additional data to support the evaluation. That included completing a 72-hour aquifer performance test, collecting infiltration rate measurements, and collecting some supplemental soil sampling for lab analyses. These activities were completed to provide us with site-specific hydraulic conductivity, porosity, density, and fractional organic carbon data. The results from these tests were generally representative of a highly permeable and low FOC sandy lithology. With all the necessary parameters in hand, we were prepared to start modeling. And so this slide shows a table of the input coefficients that the model uses to simulate PFOS transport through the unsaturated zone. Model inputs, they govern how water flows through the model domain, starting distribution of PFOS soil concentrations, and how PFOS interacts chemically in the Vadose zone. The model coefficients were derived primarily from site-specific data, except for partitioning coefficients and some chemical properties of PFOS, which were taken from scientific literature. We also chose to define the model domain with a time variable upper boundary that allows the domain to receive rainfall and a lower boundary that treats the water table as a static and fully saturated surface. As part of the model development, we completed a calibration exercise where we varied hydraulic conductivity, which is one of the model parameters, within a range of our observed values until our simulated infiltration rate matched our observed maximum infiltration rates under a fully saturated condition. Another key consideration for the model development was to decide how much rainfall would enter the model domain as recharge. So obviously in the real world, some fraction of rainfall is lost to runoff and evapotranspiration, which can be difficult to measure. However, in our simple case, we decided to use local rainfall data and assumed recharge to the water table was a constant 50% of rainfall. And that assumption was based on a regional groundwater flow model developed by South Florida Water Management District for the superficial aquifer in this area that estimated approximately 50% recharge. And our model simulated PFOS transport over a 20-year period. All right, so results. The key result from our evaluation is the PFOS leachate concentration simulated for each of our soil excavation scenarios. And this PFOS leachate concentration is simulated over the 20-year period of our model, as shown in this figure. And we'll really dive deeper into these results for each of the excavation scenarios. Before we do, it's kind of helpful to consider how soil leachate concentrations relate to groundwater concentrations. So the PFOS leachate concentration is the concentration of infiltrating water that reaches the water table, so what's percolated through the vadose. However, once that water reaches the water table, it undergoes mixing with groundwater and dilution. For our site objective of mitigating migration of PFAS-impacted groundwater, dilution is an important consideration because soil leachate concentrations greater than our leachability cleanup target level may attenuate by the time they reach down gradient monitoring points. At our site, under baseline conditions, we observed a reduction of leachate concentrations by a factor of about 2.5 by the time it reached down gradient wells, which is based on site data. All right, so going back to results, as a reminder, scenario 1 is the no action scenario where we ask what contribution of soil PFOS leaching is to groundwater under current conditions with no soil removal. PFOS leachate concentrations for this scenario is plotted as this blue line, and the dashed black line represents the provisional GCTL, kind of the ideal criteria that we're trying to reach. Under this scenario, peak PFOS leachate concentration is approximately 6,827 parts per trillion, or nanograms per liter, which is 2 orders of magnitude greater than the provisional GCTL. And as shown by the graph, our PFOS leachate concentrations are currently near their maximum, but they may, it's hard to tell in the graph, but slightly increase for another 4 years before really starting to attenuate. And after 20 years, PFOS leachate concentrations will still be greater than the provisional GCTL, even with considering dilution. That's the base no action case. Scenario 2 is excavation to the provisional leachability cleanup target level. For this scenario, we simulated removal of soil with PFAS concentrations greater than the leachability SCTL, and that's shown as the red line on this graph. Under this scenario, the peak PFOS leachate concentration is approximately 233 nanograms per liter, which is only 3 times the provisional GCTL. So removal of soil under this scenario causes an immediate reduction in PFOS leachate concentrations that reach their peak in less than a year. And after 12 years, PFOS leachate concentrations are less than the provisional GCTL and are likely going to be less than that GCTL within 5 years when you consider the effect of dilution. And finally, scenario 3 is of excavation to 5 times the provisional L-SCTL, so that's slightly higher threshold, so a little bit less soil removal. We simulated removal of soil with PFAS concentration greater than 5 times that provisional SCTL. And under this scenario, we do get an immediate reduction in PFOS leachate concentrations, but we also exhibit a slight increase until peaking, as shown as the green line on this graph, which that can be attributed to kind of vertical redistribution of PFOS mass across the Vadose zone. And the peak PFOS leachate concentration is about 1,255 nanograms per liter, which is about 18 times the provisional GCTL. After 20 years, PFOS leachate concentrations are below the GCTL, and when considering dilution, it may take about 16 years to get to that level. Compared to the no action scenario, this simulation of scenario 2, so that full excavation, and scenario 3, limited excavation, offers a reduction of PFOS leachate concentrations of 97% and 82% respectively. So these results really demonstrate a significant and quantifiable reduction in PFOS leachate concentrations at the water table in response to our simulated soil excavation scenarios. The results from our Vadose soil PFOS leaching evaluation demonstrate that soil excavation is a viable strategy to mitigate migration of groundwater impacts. Removal of soils under these 2 excavation scenarios resulted in leachate concentration reductions of 97% and 82% respectively. Additional modeling and assessment are warranted to refine the effect of that dilution on PFOS attenuation and ultimately to identify the reduction in concentrations discharging to those nearby surface waters, which is ultimately our objective. And as a next step, these data will be used to support a remedial alternatives evaluation to compare the effectiveness of soil excavation with other potential remediation technologies. Thank you.
Thank you, Dr. Munger. Do we have any questions for Dr. Munger in the audience? We've got one down here at the front that raised his hand first, if you want to grab. And then we'll go to the back there. I saw you. Right here at the front. Can you catch his mic?
There we go. How did you propose to address the contaminated soils? Where were those going to go?
Where would we dispose of them?
Yes.
In this case, it would just be taken to like a hazardous waste landfill.
So it would be haz waste. Gotcha. Thank you.
Okay, there's one towards the back there. I think you saw him.
Yeah, I'm curious. I didn't quite understand your model fits and the way those curves looked, the way you tried to explain that, because you basically you took a lot of the soil out. When you did a larger excavation, your curve's flat. You don't see any increases in the Vadose zone discharge, and then it goes down. When you took a little less out, you see this long period where it sort of goes back up again. You tried to say that's redistribution or something of the PFAS, but why wouldn't that have occurred with the larger excavation?
Yeah, I think it's in part the way that the excavation scenario is designed. So it takes like a vertically averaged PFAS concentration. And so when you have a relatively homogeneous distribution of mass at a location, obviously you're going to get a higher average soil concentration at that boring. For other borings we left in place, you might have a higher concentration near the surface. And so over time, as that water infiltrates through, you get kind of a redistribution of mass leaching and then absorbing and then leaching and absorbing until it gets finally to the water table.
Okay. So when you did the 2 scenarios, there was also a depth consideration there as well then. So in some cases you took less soil off of the surface, or was it equivalent in terms of what you did?
Exactly. So So yeah, I could add a little bit more detail about that, but basically the horizontal extents of each depth interval is a little bit different for the full excavation, whereas the hybrid excavation is just looking at a vertically averaged concentration. So it's more of a, like a cylinder of soil rather than a varying extent of soil.
Okay, thank you.
Any more? We have one up here towards the front. And then I saw you in the back. We'll grab you next. We have time.
Kind of follow up on the last question. When you decide to partially remove the soil, what depth or horizontal proportion were the most contaminated area? You got 100% out, and outsider. How do you decide partial removal horizontally or vertically? Do you have a formula to calculate based on your sampling?
Yeah, so for the full excavation, we just said we're going to excavate to the leachability criteria, which for PFOS is 7 and for PFOA is 2. And so we just look at where is the nearest clean boring for, like a 0 to 0.5 foot interval, a 0.5 to 2 foot interval, 2 to 4 foot interval. And so each interval has its own discrete extent based on that exceedance, and that's how we determine for the full excavation scenario. Oh, yeah, so for the partial removal scenario, like I kind of mentioned, it takes the full, like an averaged vertical concentration at particular borings, and if that average concentration is greater than 35, then we'll remove it. And so that's more of a vertical soil column. So there is the potential to have, some discrete intervals with higher than that concentrations left in place. But that basis for 35 was just derived on, where do we see the highest groundwater concentration impacts? And so just kind of almost like picking a number that correlates to where those impacts are and then deciding that's where we're gonna draw the boundary.
Next in the back.
Hi, so this work being done by the state of Florida, what was the motivation for, going through this amount of effort? Because that's a lot of borings and a lot of wells, and, there's something special about this site, I think, to get this kind of attention. So like, what was maybe the state's driver? And then number two, what city or town was it located in?
Yep, this is in Fort Pierce. And so, obviously, this is a priority for the state right now is identifying these sites and completing assessment to kind of really get their hands around where there is contamination. And so, we started assessment at the site, I think back in 2019, and have been kind of continually refining that until we finally, now at this point, we have our hands around everything. And kind of one of the first or highest priorities for the state at the moment is obviously, off-site migration of contamination at the site. And so that's kind of driving this first remedial step is mitigating off-site migration of contamination to that creek, which, has access, the public has access to further down gradient locations.
I think we got time for one more up here at the front.
Thank you. I'd like to piggyback a little bit off this gentleman's question, which when you send it to a haz waste landfill, are they not requiring you to do any stabilization prior to, accepting the soils that you would excavate?
I don't know if I can answer that question, but I can definitely find out and give you an answer to it.
Thank you.
Since that was so quick, we did have one more over here, if you don't mind.
Hey, Candace Beauvais with Tetra Tech. I have two questions on the technical side of things. Was that V-Leach? that you used? V-Leach for the model? What program, or did you develop something internally?
No, that was PC Progress's Hydrus model.
Got it, okay. Had a couple of choices, so I went with V-Leach first. And secondly, as we all know, the KD values are really wide-ranging. So I'm sure you probably did a sensitivity analysis in conjunction with this, but when you decide what to remove, are you using the most conservative distribution coefficient for the modeling effort?
So we used basically like I looked at a literature review that basically composited a bunch of different partitioning data into one study, and I just used kind of what their average partition coefficient was.
Thank you, Dr. Munger. Okay, so continuing on with the remediation strategies and technical advances, we move on to a technical advantage here, or advancement, with foam fractionation and impact innovation in PFAS removal from leachate by John Kroom, the Vice President of Sales and